Salam. Our chapter today is about complex numbers. We'll start with an activity to find what is a complex number and what is I, an imaginary number, pure imaginary number. We'll start by solving equations. For example, equation number 1, solve x squared minus 1 equal to 0. X squared minus 1 equal to 0, it means that x squared equal to 1. So x equal plus radical 1, which is 1, so x equal plus radical 1, which is 1, or x equal minus radical 1, which is minus 1. There is no problem with this equation. But what if we have to solve the equation x squared plus 1 equal to 0? We'll obtain that x squared equal minus 1. We used to say that this equation has no solution in R. Of course it has no solution of R, but someone invent or found a number. He said, let I an imaginary number with I square equal minus 1. Okay, so I is an imaginary number. You can't find a value of I. You never find that I equal 2 or I equal 3 or I equal minus 1 or I equal 1. There is no value of I. I is a pure imaginary number. Okay, you know the value of I square. I square is minus 1, and then you can find I cube, I power 4, but you can't never find the value of I. So if x square equal minus 1, the equation became x squared equal I squared. And you can solve this equation. You can say then x equal radical of I squared, which is I, or x equal minus radical of I squared, which is minus I. And we found what we call an imaginary number. Okay, then when they try to solve a quadratic equation like x squared minus 2x plus 2, you know that to solve a quadratic equation we need to use the quadratic formula, what we call delta, which is b squared minus 4ac. If you solve this, if you did calculate delta, you will find 4 minus 8 is minus 4. You used to say delta negative, no solution in R, but wait, you can write minus 4 as 4I squared. No, minus 1 is I squared, so you can write 4 as minus 4 as 4I squared. And now you can find two roots according to this value of delta. x1 equal minus b minus radical delta over 2a is going to be minus b2 minus radical of 4i squared over 2. It's 2 minus 2i over 2. It's 1 minus I. When they solve a quadratic equation with delta negative, they turn delta in terms of I squared, and they can find root. And when they find the root, or when they found the root, they obtained 1 minus I. Look at this number. It's called complex number because half of it is real and half of it is imaginary. Okay, when they solve a quadratic equation, they obtained a number with two parts. First part is a real number like 1, another maybe another number in another equation, and the second term or the second part is pure imaginary. It's in terms of I. As the same when they solve x2 minus b plus radical delta over 2a, they did the calculation and they obtained 1 plus I. So what is a complex number? A complex number is a number formed of two parts. First part is called real part and the second part is called imaginary part. Okay, by definition, the algebraic form of a complex number is z equal x plus iy. We call this form or this way of writing a complex number as algebraic form because we do have another forms of writing an algebraic of writing a complex number that you are going to see in the next chapter. So z equal x plus iy with a very important condition: I square always equal minus 1. In the American system, they don't write it as this. They write radical of minus 1 equal I. Okay, I square equal minus 1. Okay, x is a real number. X is the real part of this complex number denoted by Re of z, and y is the imaginary part of this complex number denoted by Img of z. So x is the real part and y is the imaginary part. For example, if you have z equal 3 plus 2i, so this is a complex number, it's formed of two parts. The real part of z is 3, the imaginary part of z is 2. Another example, if you have z equal 3 minus 2i, or 3, let's just say, change the number, 5 minus 7i. So this complex number, the real part of it is 5 and the imaginary part of it is minus 7. Part 3, z equal 2i. This complex number is formed only of imaginary part. We are going to call him pure imaginary number. We'll see that in a while. But you have to know that the real part of this number is equal to 0, while the imaginary part of this number equal to. Okay. Property 1. Okay, so we are in complex numbers. We used to write 1 as a definition, 2 properties. Let z equal x plus I and a complex number. First property, if real part of z, if imaginary part of z equal to 0, if the imaginary part of z equal to 0, then z equal x. So z equal x is a real number. But if real part of z equal to 0 with another condition, imaginary part of z not equal to 0, in this case z is a pure imaginary number. Example, z equal 5, z equal minus 3, z equal 0. These are real numbers. Another example, z equal 2i, z equal minus 5i, z equal I. We call these numbers, they are only made of the imaginary part. We call these numbers as pure imaginary numbers. Okay, let's solve an application. Write in the algebraic form each of the following complex numbers. Part A, z equal 1 plus I square. Part B, z equal 1 plus I plus 2 minus 3i. Part C, z equal 1 plus I into 2 minus 3i. And part D, z equal 1 plus I power 14. How to write these complex numbers in the algebraic form? Of course, they are not in the algebraic form, but because the algebraic form is in the form z equal x plus iy. So how to write these complex number in the algebraic form? We'll start with the first one. Usually, in this case, in this application, you only have to expand. Yani z equal 1 plus I square. It's a remarkable identity. 1 square a square plus 2ab plus b square. As you know, I square is minus 1, so the answer is 2i, and we obtained a pure imaginary number, a pure imaginary complex number. pure imaginary number. Part B, z equal 1 plus I plus 2 minus 3I. So you have to expand. Here you have to expand only by removing the brackets. You will obtain 1 plus I plus 2 minus 3I. Do we have to multiply 1 plus I by 2 minus 3I? Of course not, because there is no multiplication between the two terms. There is the operation plus. And you obtain 1 plus 2, 3, I minus 2I minus 2I. This is a complex number. Part C, z equal 1 plus I into 2 minus 3I. And we have to expand. 1 times 2. Of course we have to multiply because there is an operation times between the two factors. 1 times 2 is 2. 1 times minus 3I is minus 3I. I times 2 is 2I. I times minus 3I is minus 3I square. And then we obtain 2 minus 3I plus 2I is minus I. Minus 3I square, as you know, I square is minus 1 times minus 3 plus 3. So the answer is 5 minus I. Okay. Finally, z equal 1 plus I power 14. As you know, 1 plus I power 14 is 1 plus I power 2 all power 7. So you need to find the value of 1 plus I power 2. We already did. 1 plus I power 2 is 2I. 2I power 7 is 2 power 7 times I power 7. We don't know the value of I power 7. So how can I find I power? How can I find I power 7? 2 power 7 is, I think, 128. 128. I power 7, as you know, is I power 6 times I. So it's 128 times I power 6 is I power 2 power 3 times I. I power 2 minus 1 power 3 minus 1 times 128 minus 128I. Okay. Now let's talk about the conjugate. Part 3, conjugate of a complex number. Let z equal x plus iy, a complex number. The conjugate of z denoted by z bar with z bar equal x minus iy. So the conjugate of z equal x plus iy is z bar equal x minus iy. So you only have to change the sign of I. For example, if z equal 1 minus 3i, z bar will be 1 plus 3i. If z equal 2 plus 7i or minus 2 plus 7i, z bar will be minus 2 minus 7i. You only have to change the sign of I. For example, if z equal 1 plus radical 3, z bar equal 1 plus radical 3. You don't change anything in this case because it's a real number. There is no I to change its sign. For example, if z equal 2i, z bar equal minus 2i. Okay, this is the conjugate. Part 3, part 4, properties about the conjugate. Properties. أول شيء, let z equal x plus iy. So z bar equal x minus iy. You have to notice that z plus z bar, if you did calculate z plus z bar, x plus iy plus x minus iy plus iy minus iy, they cancel each other, is 2x. So z plus z bar always equal to x. It's 2 into real part of z. z minus z bar, if you did subtract to the two complex number, x minus x is 0, iy minus iy is plus iy plus 2iy, so z minus z bar always equal to part 2 times imaginary part of z. Finally, the most important one, z times z bar. Z times z bar is always x square plus y square, the real part square plus the imaginary part square. I can prove it. I can prove this one. As you know, z times z bar is x plus iy into x minus iy. It's a remarkable identity, is in the form a plus b into a minus b, or you can simply expand it. So I'm going to use the remarkable identity a plus b into a minus b equal a square minus b square equal x square minus I square y square. As you know, I square is minus 1 and there is a minus outside, so it's x square plus y square, and that's how we prove the property. Okay, we are going to take this property again when we have to explain the modulus. It's a very important property. Z times z bar equal x square plus y square. The first two are very logic. You can deduce them in any exercise by yourself. Another property is about the conjugate. First property is conjugate of z bar. Bar is z. Conjugate of z bar is z. Okay. For example, z equal 1 minus I. Z bar, you have to change the sign of I. It's going to be 1 plus I. Z bar bar, you have to change the sign of plus I. It's going to be 1 minus I. Okay. Second property, conjugate of z times z prime. If you have a bar between two conjugate, if you have times in the conjugate, of course z and z prime are two complex numbers. Okay, let z and z prime two complex numbers. So conjugate of z times z prime is conjugate of z times conjugate of z prime. As the same for the division, conjugate of z over z prime equal conjugate of z over conjugate of z prime. So you can always distribute the conjugate. Okay, and also conjugate of z plus z prime equal conjugate of z plus conjugate of z prime. Also conjugate of z minus z prime equal conjugate of z minus conjugate of z prime. Finally, conjugate of z power n equal conjugate of z power n equal conjugate of z. So you can always distribute the conjugate. For example, if you have z equal 1 minus I into 1 plus 5i, and without finding the algebraic form you need to find z bar. It's simply 1 plus I into 1 minus 5i. You only have to change the sign of I. Another example, if z equal for example 1 plus I radical 3 minus radical 7 and you need to find z bar, it's only 1 minus I radical 3 minus radical 7. So you change the sign of I everywhere. That's it. Okay, that's it all about the conjugate. Now we are going to talk about graphical representation. This is the last part of the complex numbers, basics of complex numbers. So complex numbers, now it's part 4 or 5 or 6. definition, properties, conjugate, properties, 6. Graphical representation. A complex number z equal x plus iy is represented graphically by a point m of affix z. We read it m of affix z. We read this as m of affix z, with m has an abscissa x, ordinate y. So if you want to represent a complex number graphically, a complex number represented by a point, with the imaginary part is the abscissa, and the real part is the abscissa, and the imaginary part is the ordinate. Example, z1, if the point z1 equal 1 plus 2i, this point m of affix z1 is the point m of abscissa 1 ordinate 2, abscissa 1 ordinate 2. This is the point m1. m1 is the graphical representation of the complex number z1. For example, if you have z2 equal 3 minus 2i, m of affix z2 or m2 of affix z2 is the point m2 of abscissa 3 ordinate minus abscissa 3 ordinate minus 2. So the complex number z2 is represented by the point m2 of abscissa 3 ordinate minus 2, abscissa 3 ordinate minus 2. This is the point m2. For example, z equal 3i is represented, z3 is represented by the point m3 of abscissa 0 ordinate 3. This is the point m3 is the point of affix z3. z5 or z4 equal minus 3 is represented by the point m4 of abscissa minus 3 and ordinate 0. Abscissa minus 3 and ordinate 0. This is the point m4, the graphical representation of the point of the complex number z4. Still, we have properties about this, about the graphical representation. Seven properties. Application. Let z equal 2 plus 3i. Represent or locate the point m of affix z, the point m prime of affix z prime, sorry, not z prime, z bar, and the point m double prime of affix minus z. If you did locate these 3 points, okay, m of affix z will be m2 3, m2 3. This is the point m of affix z. M of affix z bar is 2 minus 3i, so it's going to be m prime 2 minus 3, 2 and minus 3. This is minus 3. This is m of affix z bar. You can notice that m of affix z and m of affix z bar are symmetric with respect to the x-axis. Okay, so first property, m of affix z and m of affix z bar always are symmetric with respect to x-axis. Second thing, you have to locate double prime of f(x) minus z. Minus z is minus 2 minus 3r. You have to multiply everything by minus. So double prime is going to be minus 2 minus 3. I'm going to locate double prime minus 2 minus 3. This is double prime of f(x) minus z. You can notice that m and double prime are symmetric with respect to the origin O. So you can say that m of f(x) z and m of f(x) double prime of f(x) z minus z are symmetric with respect to origin O. This is everything about basics of complex. Next time we'll explain graphical interpretation of modulus, argument, exponential form and trigonometric form of complex number. Thank you, and I will see you.